Incorporating SIMIODE projects into a mathematical modeling course that I taught last spring. And I incorporated several projects into a mathematical modeling course. And to help students through SIMIODE projects, I wrote accompanying project assignments, and I'm going to look at examples of these accompanying projects, compare how they worked or didn't work for the modeling course, and consider what modifications could be made for future versions of the course. Okay, so since 1988, Ball State has offered a 3-credit course that focuses on mathematical models. And the course, it's Math 335 Mathematical Models, has the following course description, which hasn't changed. I checked and it hasn't changed since '88. So construction of mathematical models for use with problems in physics, chemistry, biology, and economics. It emphasizes the construction and interpretation of models. Existing computer software will be used. Okay, so the first 2 times I taught this course were in fall of 1996 and spring of 1997, and there wasn't a textbook. So I used this book called An Introduction to Mathematical Models in the Social and Life Sciences by Michael Olenek. It was published in 1978. I used that as a basis for the course. And the next time I taught the class, that was in spring of 2001, we had switched to a text by Douglas Mooney and Randall Swift. It's published by the MAA in '99. It's a course in mathematical modeling. And at Ball State, textbooks for most lower level courses are chosen by a committee. And so that's what the committee had chosen. So I adapted textbook readings to my original notes. And Mooney and Swift provide a significant amount of material to supplement class lectures. The downside is that you have to jump around in the text to match class notes. So if I wanted to use my notes as they were, I had to jump around in the text quite a bit. Okay, so the next time I taught the class was last spring, and I switched to a free online textbook I found that was published in 2021. It's Mathematical Modeling and Simulation with MATLAB by Sheldon Lee and Megan Busby. And this is some information about this textbook from the textbook. This textbook attempts to provide you with an overview of the commonly used basic mathematical models as well as a wide range of applications. It offers a perspective that brings you back to the modeling process and the assumptions that go into it. The text is designed for the student new to both computer programming and mathematical modeling. And it gives an overview how to use procedural programming in MATLAB in order to simulate and approximate solutions to mathematical models. Okay, here at Ball State, we've actually revised all of our primary syllabi for courses, and we've added in student learning objectives for each of our classes. And so here's a list of the student learning objectives for this course. So for Math 335, students will be able to create discrete deterministic mathematical models using recurrence relations and difference equations. Create discrete deterministic mathematical models using systems of recurrence relations and Markov chains. Create continuous deterministic mathematical models using differential equations. Create stochastic mathematical models using various probability distributions, uniform, normal, binomial. Determine the long-term behavior and gauge the effectiveness of mathematical models. Analyze data sets through interpolation, splines, and linear regression. So there's actually a lot of material that is covered in this course. So in order to address all of the course student learning objectives, in addition to Lee and Busby's course text, I included some material from Mooney and Swift's textbook, along with some stuff from Olenek's textbook as well. Okay, so my plan was to choose projects that would align with the material covered in class. And based on experience from my ordinary differential equations course, an ideal number of projects for the course is 6. So this is based on incorporating SIMIODE projects into my ODE class. And so my plan was to assign each project on a Friday. It would be due in 2 weeks at midnight, and each Friday's class time was used as a lab day where we'd talk about the current project and work on stuff. in class. And then students submit their lab work via Canvas. They ask them to turn in a write-up along with supporting materials. And the next two slides show my planned initial course schedule. So like what I thought the class would be. And that's the first slide. And the second slide is what the class actually ended up being. So this schedule here outlines the 16 weeks of class. There's a spring break in the middle. So it was 15 weeks for the course. And what I plan to do is spend for most of, let's see, about 2 or 3 weeks on each of these sort of subsets of topics. And as you can see, I was sort of thinking, oh, it'll be about maybe 3-ish lectures, maybe 5 if I was doing 3 weeks. And so that was my initial plan, how to cover all the material. And of course, as the semester went on, I revised the class as I was going along, and here's what it ended up turning into. So I just shifted things as needed as I was working through the class. And so what you'll see is I added some more material at the beginning of the class to help students learn. I'm saying MATLAB, but I actually had students use Octave, which is a clone of MATLAB. It's a free piece of software that you can use that essentially will do the same things as MATLAB, especially at the level I was teaching at. Okay, and then I just shifted, so we did final presentations in the last week, and so this is actually the schedule I ended up with at the end of the semester. Okay, so I had to think of some projects for the class, and since, as you can see from above, it encompasses a wide variety of topics, not all, or say many of which are not differential equations. One of the challenges in selecting project topics is that I couldn't choose them all to be involving ordinary differential equations or come from SIMIODE. So here's some initial topic ideas that I thought of that involve ODE that I was considering for the class. So on population growth and competitive species, Newton's law of cooling, and modeling the spread of a disease, and phase plane stability investigation. And here's what I ended up using for projects from SIMIODE. So I used this, one of the cool projects that is the M&M population growth. And I chose the recurrence relations portion. So I didn't use the differential equations part of that project. And there's a cool project that's Newton's law of cooling with a potato, where there's some data for a potato that is taken out of the oven, and you record the temperature every 15 minutes as it cools off. And just to give you an idea, like, so those were the topics I thought of, but the red text, I'm highlighting that stuff appeared in the course either in the lab or a quiz. And then the M&M population growth, that actually got used throughout the class in various topics. So almost everything I was thinking of incorporating was incorporated in some fashion. The only thing that wasn't was this modeling the spread of a disease. Okay, so here's and the next two slides are gonna give you an idea of the projects that we ended up working on in class. And so in the first column, that's kind of what the lab is, or the overall topics I wanted to introduce. So we first started with modeling concepts and introducing MATLAB, and then the second lab was on MATLAB concepts and recurrence relations. And then we did discrete models for our third lab. And then in the second column, there's the problems I gave the students. I'm summarizing them. And then there's a topic description in the third column. And I highlighted, I think that's purple, some color you can see. That's the part that involves the SIMIODE project. So the def and immigration with M&Ms, we did that in lab 2. And then this was using recurrence relations to model M&M population growth. Okay, and then the other stuff is all sorts of things that I incorporated into the class based on the material that we were learning about. Okay, and then here's the fourth, fifth, and sixth labs. So we looked at continued models, stochastic models, and empirical models. And again, the purplish colored text, that's the part that incorporates SIMIODE material into the class. So we looked at the Newton's law of cooling, and we looked at the models. We looked at models for cooling a potato that involved Newton's law of cooling. And I also incorporated differential equations where we looked at spring mass systems and a second order, the harmonic oscillator equation. They investigated that. Okay, so just like I did for my ordinary differential equations class, for each portion of a lab based on a SIMIODE project, I wrote up an accompanying set of instructions. So I actually have learned that in order to help with the students working through the material, I write up a set of instructions based on the SIMIODE project to guide the students through the project and maybe add some extra things in I'd like them to look at. Okay, yeah, so these instructions were designed to help students be guided through each SIMIODE project. Okay, so the first thing we looked at in lab from SIMIODE is the death and immigration with M&Ms project. And so I wanted them to read this is the student version of the project, that handout. And then following the instructions in the handout on pages 1 and 3, I wanted them to perform the experiments for M&M death and M&M death and immigration and record the results in tables 1 and 2. And information from these tables will be put into the work the students are turning in. And I also, because I actually have given this project to students during the COVID era with the pandemic, so we were doing everything virtually. So there's actually um, slides that illustrate doing the experiment virtually. So you can go through each slide in a PDF file and look at how the M&Ms are removed at each step. The up-Ms you take out, those are considered to have died. For that, the initial number of M&Ms is 55. Okay, I also for this, I also chose an integer k from 6 to 16, and I repeated the M&M death and immigration experiments. For that, you toss out M&Ms, remove the up-Ms, and then you add a fixed number back in that models immigration back into the population. And instead of using 10 for the immigration number, like in the second experiment, I used a different number, which I didn't tell the students what it was. It was a number between 6 and 16. And so I provided them with the data from me doing the experiment. And so they were supposed to use this data as part of their project. And so here's the things I wanted them to do. First of all, and this is based on the SIMIODE project. So can you think of functions A of n and B of n to model the data you collected for each of the first two experiments? And if you're not able to do so, that's okay. This is hard to do directly. So we talked about this in class. And then, as discussed in the handout, another way to approach this is to find a relationship between the number of M&Ms at a given iteration in terms of the number of M&Ms at the previous iteration. So I was bringing in the idea of recurrence relation. And so here's a suggested model for the second experiment. It's the recurrence relation b at n plus 1 equals 0.5 times b at n plus, okay, there's a typo there. That should be 10 for n bigger than or equal to 0. And this is equation 1 on page 5 of the handout. And we also need a starting point. And so at time step n equals 0, we had 50 M&Ms we started with. And for the virtual experiment, b at 0 is 55. Okay, so then I asked them to find the students to find a recurrence relation of the form a at n plus 1 equals some function of n for n bigger than or equal to 0 to model the first experiment with the appropriate initial condition for n equals 0. And then I asked them to create a table to display the information from table 1, that's the first experiment, as well as a third column with the outputs for your model for each choice of integer n. Do the same thing for the information from table 2 for the second experiment. And I wanted them to include these tables they create in their answer for the question. And compare your models for experiments 1 and 2 to the data you collected. How well do they agree? And I wanted to justify their answer mathematically. And then in this project, it's discussed like you can use Mathematica's rsolve command to solve a recurrence relation. And so I showed the students how to do this. I also showed them Wolfram Alpha, which you can use to solve things if you don't have a copy of Mathematica. The only issue there is that not all Mathematica commands will work in Wolfram Alpha when you type them in explicitly as you need them for Mathematica. So you may have to modify the commands. And then I asked students to answer, does your answer agree with that in the handout? Why or why not? And then I wanted the students to solve the recurrence relations, the one they found for the first experiment using Mathematica or Wolfram Alpha. So, okay, so first of all, I want them to solve the first two recurrence relations. using technology. Then I wanted them to go back and resolve them by hand without using the rsolve command. And then I wanted them to set up a model for the data they got from the third experiment that I gave them, and make a function C of n to describe what's going on here. And there's an unknown parameter for the immigration number K. And then this YouTube video here is a nice introduction to this Excel solver. And so I wanted them to watch that to learn about the solver. I actually showed them how to use it in class as well. And so then the goal was for the students to use the solver to try to set up a model for the third experiment and then figure out what the parameter K is. Okay, and then they're supposed to talk about how well does their model fit the data and justify their answer mathematically, and then report on what they think the number K should be that I chose for table 3. Okay, so that was stuff embedded in lab 2. And then the next thing I wanted students to do in lab 4 was this is using Newton's law of cooling. So read the potato cooling handout, and then this is a reference to a textbook I use for teaching differential equations. It's written by jury level, and so if you go to that link, you'll learn about Newton's law of cooling if they hadn't seen it before, for cooling a cup of coffee, and you can use this for modeling the potato as it cools. And so mathematically, Newton's law of cooling can be written as du dt equals k times m minus u, or use the temperature of the potato at time t. M is the ambient temperature, and k is a proportionality constant. And so then I wanted them to make a table. So the first 2 columns would be a time, and then the temperature of the potato goes in the second column. And then I wanted to add a third column that computes the difference between the air temperature and the potato's temperature for each given time. Then I wanted them to add a fourth column that estimates the derivative with respect to t at each time. And the times were given in increments of 15 minutes. And then using information in the third and fourth columns, I wanted the students to find an estimate for this proportionality constant K, and then they should include work for finding this estimate. Okay, then I want students to set up an initial value problem for the temperature of the potato, U of t at any time t bigger or equal to 0, and solve this initial value problem. Then talk about how well does the model solution match the measured data, and then estimate at what time would the potato reach a temperature of 98.6 degrees Fahrenheit using their model. And then answer, does this seem like a reasonable answer? And the next thing I want them to do is just consider, what if they had never heard of Newton's law of cooling, but you knew that a differential equation could be used to model the data given. And if you use the second column, which is the temperature of the potato, and the fourth column, which is an estimate for the derivative, you can use this to construct a differential equation. You basically just got it. One of the ways you can do this is draw a scatter plot of the data and figure out how the two quantities, the derivative and the temperature, are related to each other. And then students are supposed to set up an initial value problem with the differential equation found in part F, solve this initial value problem, and compare the solution that students got to the initial value problem in the question 1B. And then again, answer how does your second model solution match the measured data. And next, I asked students to say, well, what if the solution was U of t is of the form a plus b times e to the negative ct, which looks like what they should be getting for the solutions to the previous 2 versions of the model. I want students to find values for a, b, and c that produce a better model than those found in questions 1b and 1g. My intent there was for students to try to use the solver. And then I asked, how well does your third model solution match the measured data and justify our answers mathematically? So that's all stuff I asked them to do with just looking at how the potato was cooling over time. This next question here, this is something I've given in various forms. This is basically, solving, I have Inspector Columbo, and I use the characters from the game Clue. And so Columbo is this police inspector, and Professor Plum is you're trying to figure out how Columbo can determine that Professor Plum is lying and he killed Mr. Body. And so this is a nice application of Newton's law of cooling. Okay, so that's stuff I incorporated from SIMIODE. And then another place that SIMIODE could be brought in is by means of the final projects that I give students for the class. So for this, I'm going to give you kind of an outline of what I assigned to the students. So this is a way that students could pick final project topics that come from SIMIODE. And so students' final project is based on a group project, and I want students to work in groups of 2 to 4, and I help them find a group if they didn't have one. And the project is supposed to involve the study of a topic related to our course, a presentation of the topic to the rest of the class, and a handout on the topic prepared by the group. And it was up to the group to decide how to present their topic. And I suggested PowerPoint, or there's a whole bunch of PowerPoint like free things out there that, and that this web link gives, I think, an example of 17 different things you could use. And the requirements I had were each person in the group would be expected to contribute to the presentation a portion of the material related to the group's project, including presenting for 5 minutes. Whatever project the group chooses must involve mathematical models. And then I gave them a bunch of places you could look for things. I used the SIMIO website, COMAP resources, the Cody journal, a link to a linear algebra book, and a link to a set of projects published by the MAA that used calculus for modeling projects. And then the College Math Journal, Math Magazine, American Mathematical Monthly, American Journal of Physics, and then JSTOR. These are all cool places where you can find modeling related projects. Okay, now I will admit that I'm somewhat biased in this is a bunch of examples of things you could use, and I've actually used this in my differential equations class. But these are, numerical methods, mechanical vibrating, Kepler's laws, things like Richardson's arms race model, electrical circuits, terminal velocity, Van Meegeren art forgeries. This is stuff from a book by Martin Braun. This also comes from Martin Braun's book. I'm looking at shark populations in the Mediterranean. Competitive exclusion, detecting diabetes, some competitive hunters, Locke and Volterra, and then Tacoma Narrows Bridge. So these are things that I suggest the students could also pick things that weren't on the list. I just wanted them to check with me ahead of time. Oh yeah, an earthquake shaking. And here's the topics that were chosen last spring. All but predicting a country's global soccer ranking involve differential equations. And this blue whale and crow population model, that comes from the Cody journal. Okay, so here's what I noticed about the class. One of the main obstacles for students besides the math concepts was the software involved. Students were familiar with Excel, most of them. Most had not encountered the solver. And MATLAB or Octave and Mathematica were a more challenge for many of the students. And Wolfram Alpha also caused some unexpected problems. A lot of students use this instead of Mathematica. And one of the problems is complex Mathematica commands entered in Wolfram Alpha don't work. And it seemed like in previous years, some of them actually did. I will say this is typical for students in most courses that use software. And initially, students struggle with the projects, and as the semester progressed, they got the hang of the projects. And I had to provide liberal hints, especially with the projects involving the Excel solver and Octave. And a lot of time, much of the for lab days, much of the time was spent working through portions of the lab with students. And overall, students seem to do well in the course. So next time I teach the class, I want to continue with the SIMIODE projects. I want to try to incorporate more if I can, if possible. Here's some things I've thought of, and there's actually links to the SIMIODE page for each of these projects here. I want to continue the practice of working with students on projects on lab days, and then Ball State has these interactive learning spaces that might be more conducive to this setting than a traditional classroom. Okay, so that's, I think, where I'm going to stop. I actually have some more slides that involve like how I use the M&M data we collected in class to illustrate some statistical ideas like mean and variance and standard deviation. But if you look through the slides, which I expect will be posted, you could look at that part too. So I think I'll stop here.